Hello, this is a follow-up to Chapter 7 for Integrated Math 3. This section that we're going to be talking about is technically actually in Chapter 10. It's section 3.3 of Chapter 10 where they talk about the natural log. For our class, we chose to bring forward the conversation about the natural log to complement the Chapter 7 where they introduce the common log. The natural log has connections in the real world, in particular in continuously compounded interest. And so the natural log is often referred to as the ln. And so the symbol for the natural log is ln. It's one of the two log buttons that we have on our calculator. And that natural log really is the same thing as log base e. And e is just a number. E is actually an irrational number. And if you plug that into your calculator, you would get an approximation for it. For now, it's important just to recognize it is a number. Just like pi is a number, e is a number, and it's approximately 2.718. Remember it to that much clarity is sufficient enough. So again, the natural log is log base e. So we can graph these functions, the natural log, just like we can graph log base 10. So we'll do that towards the end of this lesson, but I just wanted to bring that up, that again, e to the x and the ln of x are also inverse functions of each other as well. So again, what I was saying is that if we have y equals e to the x, that's an exponential function. The base is e, and it has an inverse. E to the x's inverse function, abbreviated y inverse, would be the ln of x. And so while these two functions are inverses of each other, e to the x and the ln of x, they also undo each other. And so we'll be talking about that as we move forward, but this section in Chapter 7 is not really about graphing logarithms, but really converting in between equivalent forms and using the three properties of logs: power property of logs, product property of logs, and quotient property of logs in order to rewrite in expressions in equivalent forms and also to even solve equations. So the first section that we'll go over will be to convert in between equivalent forms. So if you start with an exponential form of e cubed equaling x, again, e cubed is 2.718 times itself 3 times, but I could write that in an equivalent logarithmic form. So the equivalent logarithmic form I will write over here in the next column. Again, this is its equivalent form. Can be written in a different way, and that different way that this could be written, again, would be log, and then the base of this exponential is e, so that would be log base e of the answer x equals 3. But the thing is, we don't write log base e. Instead, we abbreviate that is the same thing as the ln of x. So this is really the ln of x equals 3. And this is the same thing. So these two represent the same relationship. This is asking when does the ln of x, which is again a function, a curve, when does that output a 3? So what would be that input? And that input would be e cubed. So, and the next example that we'll go over is when it looks a little bit different. If you are given now e to the x, which is kind of like it's a function, and now we're trying to figure out when does that output 36. So when does it intersect perhaps a horizontal line, or when does it output 36? And so if, again, I work to rewrite that in an equivalent form, I think that, again, from our work with other logarithms, we think that this is the same thing as log base e of the answer, right? Log base e of the answer being 36 equals the exponent. But again, log base e is really the same thing as the ln of x. So this is really the ln, but this time the argument is 36. So the ln of 36 equals x. So again, the point is that here and here, these two are equivalent equations. Okay, and so the next thing that we will go over is starting from a different perspective. If we're starting from a logarithmic form and you're trying to rewrite that in its equivalent exponential form. So if we have the ln of 53 equaling x, how do we go now the other direction of writing its equivalent exponential form? Again, this is log base e. Now again, of 53 equals x. So again, the base is e, so I can rewrite this as the base is e. The exponent, right, is what comes out of the log, and then what's inside is the answer. So this is the same thing as e to the x equals 53. So these are again equivalent. One more example would be if you have the ln of x equals 18, then I can rewrite that in its equivalent form as, again, log base e of x. So the base here is e. The exponent, or the power, is what comes out, and then again equals x. So these again are all equivalent. What you're also going to be doing in this lesson is also to simplify expressions using log properties. So the log properties that apply to every other log base also apply to the natural log. So again, there's a power property. There is going to also be a product property, a quotient property. So we will go over a couple of examples in this particular section. So if you are in part 2 of the work today where you're asked to condense into a single log, we'll go through a couple of examples. So here is the first example under condensing umbrella when we have the ln of 4. And again, we don't have to write the argument in parentheses. Sometimes it will look like that, sometimes it won't. And the ln of 3x. So again, when I see this plus sign here, that is a reminder that here, this tells me I will use the product property of logs because I see the addition of logs with the same base. So I can combine these into one base, being the ln, right, because that's log base e. And now I'm using the product property where I take each one of the arguments, the 4, and then now this becomes times 3x. And then I can again close my parentheses. So these two things are equivalent. Simplifying this a little bit further, this is again the same thing as the ln of 12x. So that is again my final answer. For a second example in this same section where again you're asked to condense a log, I'm going to now use the power property for the next example. So example number 2 in this section is if you have 1/2 the ln of 256 minus 3 times the ln of 2. So for this particular example, again, here I see subtraction, but as a reminder, we've got to do order of operations for simplifying logarithms. Order of operations means before I do the subtraction problem, I've always got to deal with these multiplication problems first. These multiplication problems mean I will use the product property of logs. So first, I'm going to do the product property. Again, first, I will use the power property of logs. And so if I use the power property of logs to simplify this, I will rewrite this in its equivalent form as the ln of 256 to the 1/2 power minus the ln of 2 to the 3rd power. Now, one of the very important things to remember about the 1/2 power, that is the same thing as the square root. So the 1/2 power is a fractional exponent, and it's the same thing as the square root. And so when I'm actually now finally simplifying this, this will be equal to the ln of the square root of 256 is 16, and then subtract the ln, and the 2 cubed is 8. And now when I see again this subtraction here, now I will use the quotient property of logs. Again, the quotient property of logs means to divide. The quotient property of logs means I will divide the arguments under one log. So this simplifies to the ln of, now it will be the 16 divided by the 8. And then I can close my parentheses and finally simplify. This is the same thing as the ln of 2. And that is my final answer for this particular problem. I will go over one other case where now we're expanding the logarithm. And so the expansion of something is when you again make it larger. And so condensing was what we were just doing on the previous example when we made something smaller and to condense it under a single log. Now we're going to expand into multiple logs. So here is our first example. If we have the ln of 2m to the 8th power. Well, again, one of the things to recognize is that even though it's not written explicitly here, there is a multiplication operation happening in between the 2 and the m that is being cubed. And so I can separate this first by using the product property. So we will decouple it by using the product property of logs first. And so this is really the same thing as the ln of 2. The product property is when you add the logs that have the same base, and then we're using the ln of m to the 8th. The next thing that we can do to continue to expand the log and simplify it pretty much as much as we can is to use the power property next. And the power property was when we knock that 8 down into the front. And so this is the same thing as the ln of 2. Again, plus, now we would have 8 times the ln of m. And that is in its fully expanded state. These are expressions, so we're not looking to figure out a final value. We're just looking to write them in another equivalent form. The final example that we will go over today is if we have the ln of m to the 5th power divided by n squared, all raised to the 3rd power. Again, it's the ln of m to the 5th divided by n squared, all raised to the 3rd power. Well, the first thing that we've got to do when we, again, are dealing with simplifying any expressions is, can we consolidate anything inside of the parentheses first? Can we simplify them? Can we combine any like terms? Here we cannot. So the next thing that we do is to actually use, again, the power property to bring this into the front. So first we will use the power properties to rewrite this as 3 times the ln of m to the 5th divided by n squared. So again, my first step was to use the power property of logarithms. The next step that I will do, and I have to be careful, is that this 3 is going to apply to that entire quantity. So I'm going to use the quotient property next because I see a division problem here. So second, we'll use the quotient property of logarithms to rewrite this. So this is really the same thing as 3 times, and now breaking this up, I'm going to use these more funny looking brackets, that this is the same thing as the ln of, again, m to the 5th, and then quotient property means subtraction in between the logs of the same base, and then this would become, whoops, that should have been n squared, not m, ln of n squared. So notice that again, because I saw division, I used subtraction in between them. And finally, I could use the power property again because I see an m to the 5th. But being careful with the fact that there's a 3 that applies to everything here. So this is really the same thing as 3 times, again, I'll just keep it here in the parentheses, 5 times the ln of m. And again, we've got minus. But now this 2 comes down in the front because I'm using the power property to knock that power down. And now we have the ln of n. And so now with my brackets here, you can see that this is going to actually distribute. This 3 will distribute here, and it will also distribute here as well in my final simplification. So my final simplification is this is equivalent to 15 times the ln of m, take away 6 times the ln of n. And that is a fully expanded logarithm.